Hello world, it's Siraj, and today we're going to generate words. So given some book or movie script or any kind of text corpus, it's plug and play, so you can give it any kind of text corpus. It will learn how to generate words in the style of that corpus of text. And in this case, we're going to give it a book. The book is called Metamorphosis by Franz Kafka, which was a really crazy, weird writer from the 20th century. Anyway, he's a cool dude. Anyway, we're going to generate words in the style of that book. And this can be applied to any text, any type of text. It doesn't just have to be words. It can be code. It can be HTML, whatever it is. But that's what we're going to do. No libraries, just numpy. So I'm going to go through the derivation, the forward propagation, calculating the loss, all the math. So get ready for some math. Put on your linear algebra and calculus hats, okay? So this is kind of what it looks like, this first image here. And I'm gonna actually code it as well. So I'm not just gonna glaze over, I'm gonna code it. So we can see the outputs as I go. But the very end part will be, I'm gonna code the important parts. Let me just say that, okay? So check this out. Given some text corpus, it will predict the next character. So what you're seeing here is it actually predicting the next word. But we're gonna do a character level recurrent network. So that means it's gonna generate character by characters. Okay, so character by character by character, not word by word by word. Okay, so it's gonna be trained for 1,000 iterations. And the more you train it, the better it's gonna get. So if you leave this thing running overnight on your laptop, then by the time you wake up, it'll be really good. However, I wouldn't recommend training it on your laptop. As my song says, I train my models in the cloud now because my laptop takes longer, right? So what is a recurrent network, right? What is this thing? We've talked about feedforward networks. I've got two images here of feedforward networks. The first image is the most popular image, right? It's that really funky looking neuronal architecture, but it can be kind of confusing if you think about it, because it's not like these neurons are classes and these classes have links to all of the other neurons, like it's some kind of linked, massive crazy linked list kind of thing. No, or tree-like thing. It's not really like that. What's really happening are a series of matrix operations. So these neurons are the output of a series of matrix These neurons are actually just numbers that we then activate with an activation function. So a better way of looking at it would be as a computation graph, a more mathematically sound way of looking at it. So if you have some input, and the input could be anything, what you would do is you would multiply the input by the weight matrix, add a bias value, and then activate the result of that. And that would be your output that you then feed into the next layer. A layer, what you see as these neurons, a layer is actually just the result of a dot product operation followed by adding a bias value if you want to add a bias, which you should in practice, you should add a bias. I've built neural networks without biases before for examples, but you really should add a bias, and I'll talk about why in a second. But you should add a bias value, and then you activate the output of that. And by activate, I mean you take the output of that dot product plus bias operation, the output of that, and you feed it into an activation function, a non-linearity, whether that's a sigmoid or tan H or rectified linear unit. And the reason we do that is so that our network can learn both linear and non-linear functions, because neural networks are universal function approximators. If we didn't apply an activation function to it, it would only be able to learn linear functions. We want it to learn non-linear and linear functions, and that's why we apply an activation function to it. Now, a great way to remember this whole thing is to just rap about it. So input times weight, add a bias, activate, repeat. Here we go. Input, sing it with me, times weight, add a bias, activate, repeat, and you just do that for every layer. You just repeat that process, okay? So feedforward networks, they're great for learning an input-output pattern. What is the rule here between the set of inputs and the set of outputs, right? And in the end, a feedforward network, and in fact all neural networks, it's just one big composite function. What do I mean by that? I mean that you can think of a neural network as a giant function, and inside of that network are smaller functions. nested functions. A composite function is a function that consists of other functions. What do I mean by nested functions? Remember this computation graph that we just looked at right here? These are all functions. Each layer is a function, right? Input times weight, add a bias, activate. That is a function that you feed the output of as the input to the next function. So what a neural network is, so the most nested function, right in the middle, this most nested function is the first layer value, whose output we then feed to the next layer, which would be the next function, whose output we feed to the next layer. So the largest function, the function on the outside here is then the output layer, because we're feeding it the inputs, output, the output of all that chain of computation that already occurred. Right, so that's what that is. So it's a composite function, and we would use feedforward nets anytime we have two variables that are related: temperature, location, height and weight, car speed and brand. These are all mappings. But what if, dun dun dun, I'm just adding my own sound effects, dun dun dun, what if the ordering of the data mattered? Right? What if you had stock prices, right? This is a very controversial topic, but I just, the stock price thing gets a lot of views, even though I don't really personally care about finance data, but I know some of you guys do, and I'll probably talk about it more in the future. Anyway, tangent. Back to this. What if the time matters, right? So stock prices are a great example of when time matters. You can't just predict a mapping between time and the price. What happened before, what the stock prices before, are what matter to the current stock price. That's actually debatable in the context of stock prices, but it applies to all time series data. So video, right? If you want to generate the next frame in a video, it matters what frames came before it. You can't just learn a mapping between a frame and the time that frame shows up, because then what happens is, given some new time, you can't just generate a frame based on nothing else, right? It depends on the frames that came before it. You see what I'm saying? The sequence matters. The sequence matters here. The alphabet or lyrics of a song. You can't just generate a lyric or an alphabet depending on the index that it's at. You've got to know what came before it. Try to recite the alphabet backwards. And so to get into neuroscience for a second, try to recite the alphabet backwards. It's hard, right? Z, Y, X, W, Q, U. Okay, see, I can't even do it right now. I'm not going to edit that out. So, or any song, try to recite a song backwards. You can't, because you learned it in a sequence. It's a kind of conditional memory. What you remember depends on what you've stored previously, right? It's conditional memory in that way. And that is what recurrent networks help us do. They help us compute conditional memory. They help us compute the next value in a sequence of values. So that's what recurrent networks are good at. That's what they're made for. And it's not like this is some new technology. Recurrent networks were invented in the 80s. Neural networks were invented in the 50s. But why is this super hot right now? Why are you watching this video? Because with the invention of bigger data and bigger computing power, when you take these recurrent networks and give them those two things, they blow almost every other machine learning model out of the water in terms of accuracy. So it's just incredible. But anyway, this is a picture of a three-layer, this is a picture of a three-layer recurrent network, right? So you've got your first layer, which is your input, your hidden state, your output layer. And so that would just be a feed-forward network. But the difference here is that we've got this other layer right here, and that is, so what that other layer is, it's not actually another layer. The difference is that we've added a third weight matrix. So we've got our first weight matrix, our second weight matrix, but we've got a third weight matrix, and that's really what makes it different than a feed-forward network, is that we're adding a third weight matrix. And what the third weight matrix is doing is it's connecting the current hidden state, so the hidden state at the current time step to the hidden state at the previous time step. So it's a recurrent weight matrix, and you'll see programmatically and mathematically what I'm talking about. But that's really the key bit here for recurrent networks. That's what makes it unique from feed-forward networks. And so what this does is whenever we feed in some value, because we are training this network, right? We continuously feed it new data point after data point from our training set. But for feed-forward networks, we're only feeding in the input. We're not feeding in the previous hidden state. We're only feeding in input after input after input, and the hidden state is being updated at every time step. But because we want to remember a sequence of data, we're going to not just feed in the current data point wherever we are, we're also going to feed it in the previous hidden state, and that is, and by that I mean the values that are computed from the previous time step for that hidden state, right? That set of numbers, that matrix. And so you might be thinking, wait a second, why don't we just feed in the input and then the previous input as well from the previous time step? Why are we feeding in the input and the previous hidden state? Because input recurrence only remembers what just happened, that previous input. But if you feed it in the previous hidden state, then what's happening is it can remember that sequence. It's not just about what came right before it. It can remember everything that came before it. Because you can think of that hidden state as a kind of think of it like clay that's being molded by every new input. It's being molded by every new input. And by feeding that clay that's being molded back into the network, it's learning neural memory. So it's a form of neural memory, conditional memory, and it can remember sequential data. So, right, so here's another example, just to give a few more examples before I go into the code here. But we have, so this is a very popular type of image for recurrent networks. So what's happening is, we're feeding in the current input, calculating a hidden state, and then computing an output. And then for the next time step, we're giving it that new data point as well. And so the blue arrow is what's different here compared to a feed-forward network. We're feeding in the previous hidden state as well as the input to compute the current hidden state to compute our output, our Y value. And we're using a loss function to improve our network every time. And so if you think of what that recurrence looks like, it looks like this. So remember that feed-forward network we just looked at? The difference here is that we are feeding in the output of the hidden state back into the input, the output of this weight times bias activate operation that's in a layer. Okay, so the formula for a recurrent network looks like this, which basically says that the current hidden state, HT, is a function of the previous hidden state and the current input. Okay, and then the theta value right here are the parameters of the function. So the network learns to use h of t as a lossy summary of the task relevant aspects of the past sequence of inputs up till t. The loss function that we're going to use here is going to be the negative log likelihood. Okay, this is a very popular loss function for recurrent networks, like plain old recurrent networks, not using anything fancy like long short-term memory cells or bidirectional capabilities. But the negative log likelihood usually gives us the best output or the best accuracy for plain old recurrent networks, which is why we're going to use it. And we'll talk about what that consists of in a second. But our steps for this are going to be to first initialize our weights randomly, like we always do, and then we're going to give the model a char pair. So what is a char pair? The char pair is going to be the input char, so that's some seed, some letter from the training text that we want to give as input, as well as the target char. And the target char is going to be our label. So our label is actually the next char. So if we take the first two chars from some input text, from some input corpus, let's say the word is the input char would be T, then the target char would be H. So given T, we want to predict H. So you see how that target char acts as our label that we're trying to predict. And so once we have that H, we can compute the most likely next character and then compare from our forward pass. We're going to calculate the probability for every possible next char given that T according to the state of the model using the parameters. And then we're going to measure our error as the distance between the previous probability value and the target char. So that's what acts as our label, the next char in the sequence. And we just keep doing that. So it's a dynamic error, right? And so once we have that error value, we'll use it to help us calculate our gradients for each of our parameters to see the impact they have on the loss. And that is backpropagation through time. And we call it through time because we are using that hidden state to hidden state matrix, that recurrent matrix value. But otherwise, it's just the same. It's just backpropagation. It's called through time because we are applying that hidden state to hidden state matrix to it. Okay, so then once we have our gradient values, we're going to update all the parameters in the direction in the right direction to minimize the loss. That's gradient descent via our gradients, and we just keep repeating that process. So everything is the same here. Gradient descent as a feedforward network. Gradient descent, calculating an error value, a forward pass, but the difference is that we are connecting the current hidden state to the previous hidden state, and that changes how the network learns. So what are some use cases? I talked about time series prediction, specifically weather forecasting, yes, stock prices, traffic volume, sequential data generation as well, music, video, audio, any kind of sequential data. What is the next note, the next audio waveform, the next frame in the video? Okay, and then for other examples, I've got a great one here for binary addition that was originally invented by Trask, who's a great technical writer. Definitely check that out. And so once we understand the intuition behind recurrent networks, then we can move on to LSTM networks and bidirectional networks and recursive networks. Those are more advanced networks, and they solve some problems with recurrent networks. But before you get there, you gotta understand recurrent networks, okay? So this code contains 4 parts. The first part is for us to load the training data, then we'll define our network, then we'll define our loss function, and the loss function is going to contain both the forward pass and the backward pass. So the real meat of the code is going to happen in the loss function. And what it's going to do is it's going to return the gradient values that we can then use to update our weights later on during training. But the meat of the code is going to happen in the loss function. And once we've defined that, we'll write a function to then make predictions, which in this case would be to generate words, and we'll train the network as well. Okay, so our first step is going to be to load up our training data. So to load up our training data, I'm going to say, okay, so let's define what that data is, by the way. So if we open this file, we'll look at it, kafka.txt. It's one morning when Gregor Samsa woke up from troubled dreams, blah, blah, blah. Right? So this is just a book. It's a big book, a big TXT file. That's what the input is going to be, okay? So we'll open it up using the native functions here of Python, and it's going to be recursive because we want all of it. We'll just read that simple plain TXT file, and then we're going to say, okay, let's get that list of data points or chars. In this case, we'll store it in chars, and we'll define how big our data is as well as our vocab size. And we can say that it's going to be the length of the data, that big text file, as well as the length of the chars. How many chars do we have? And we'll print it out for ourselves just so we know how many chars there are. And once we've done that, we can go ahead and print it out. And it's going to tell us how many unique chars there are, which matters to us because we want to make a vector of the size of the number of chars that there are. So let me go ahead and print that out, and it's going to tell us exactly what the deal is. And so we've got, that's how many characters it has. Okay, so the data has 137K characters, and 81 of them are unique. Okay, good to know. Our next step is to calculate the vocab size. Okay, so we're going to calculate the vocab size because we want to be able to feed vectors into our network. We can't just feed in raw string, chars. We've got to convert the chars to vectors because a vector is an array of float values in this case, or a vector is an array, a list of numbers in the context of machine learning. And so we'll calculate the vocab size to help us do this. So we're going to create 2 dictionaries. And both of these dictionaries are going to convert the characters to integers and then the integers to characters, well, respectively. One will convert from character to integer, which is the one that I've just written. And then the next one is going to say, let's convert the integers to characters. And once we've done that, we can go ahead and say, well, let's print all of the values that it's storing, because these are our dictionaries that we're going to use in a second to convert our values into vectors. So let's go ahead and print that. And what's the deal here? Oh, enumerate, right? Enumerate. Great. right? So here are our vectors, right? It's a dictionary, or here are our dictionaries. One for characters to integers and one for integers to characters. Okay, so once we have that, now, so we've done that already. And so then we're going to say, let's create a vector for character A. So this is what vectorization looks like for us. So let's say we want to create a vector for the character A. So we'll say we'll initialize the vector as empty. So it's just a vector of zeros of the size of the vocab. Okay, and so of the size of our vocab. And then we'll say, okay, so convert the, now we're going to do the conversion. We'll say char to integer. So A to the integer. So that's going to be our input. It's going to give us an integer value, and we're going to set it to 1. And so what happens is when we print out this vector, it's going to be a vector of size. Let's see if I got that right. So it's going to be a vector of size. Hold on. Oh, right. Import numpy. Duh. I forgot importing numpy. Yeah. Okay. Right, so it's a vector of size. How many unique characters were there? There were 81 unique characters. So it's a vector of size 81, and all of those values, all of those elements in the vector are going to be 0, except for the one that is the mapping between A and its respective integer in that dictionary. So that's how we mapped it. That's why we created those two dictionaries. So this is what we would feed in as A. So we will feed in 2 of these, because remember I said that we have a char pair. So we'll feed in A and whatever the next character is as our input, which would be our input and our label value. And the label is our other character, our next character. Okay, so then for our model parameters, we're going to define our network. Remember, it's a 3-layer network. We have our input layer, our hidden layer, and our output layer. And so all these layers are fully connected. So that means every value is going to be connected to every other value between layers. Okay, so the way we'll define that is to, well, first let's define our hyperparameters. We got to define our tuning knobs for the network. So we want to say that our network's going to have 100 hidden neurons for its 100 neurons for its hidden layer, and then we're going to say that we want there are going to be 25 characters that are generated at every time step. That's our sequence length, and then our learning rate is going to be this very small number. Because if it's too slow, then it's never going to converge. But if it's too high, then it will overshoot and it's just never going to converge. The learning rate, by the way, is how quickly a network abandons old beliefs for new ones. So if you're training your neural network on cat-dog images, the lower the learning rate, the less likely it'll be to, when given a new dog picture, if you've just been training it on cat pictures, if you give it a new dog picture, the less likely it'll be to consider that as a part of the training data. If you're trying to be able to recognize both, the lower the learning rate, the more likely it will consider that dog picture just an anomaly and just kind of discard that internally. So it's a kind of way to tune how quickly a network, abandons old beliefs for new ones. That's another way of putting it. Anyway, so that's for our hyperparameters. Now we'll define our model parameters, right? We've defined our model parameters, and now we can define our network's weight value. So the first set of weights are going to be from our input, so X, so WXH, so X is our input. This is what the terminology is, right? So the weights from our input to our hidden state, right? So that's going to be initialized randomly using the numpy's random rand_n function, and it'll be a value between the hidden size that we've defined and the vocab size, because those are the two values that we're dealing with here. And we'll multiply it by 0.01 because we just want to scale it for a character level recurrent network, because it's a character level recurrent network. So input to hidden state. And so then we will repeat that process, but this time for our, not from our input to hidden, but for our hidden state to our next hidden state. And so that's our recurrent weight matrix right there. That's our recurrent weight matrix. And so lastly, we'll have our third weight matrix, which is our, what's our third weight matrix? Our third weight matrix is our hidden states to our outputs value, our output. And so that's going to be vocab size to between the vocab size and the hidden size. And then we will also, since we have two biases, we'll say the bias for our hidden state will be initialized as a set of zeros of the hidden size, because it's for our hidden state. And then we will, so that's our hidden bias. And one more bias, and that is for our output bias. That is our output bias. Also a collection of zeros. The difference here is that is of the vocab size. Okay, and so, yeah, great. Uh-oh, let's see what we got here. Hidden size is not defined. Hidden size is right here. Compile. What's the deal? Hidden size is not defined. Yes, it is. Yes, it is. Invalid syntax. Great. So the function is going to take as its input a list of input chars, a list of target chars, and the previous hidden state. And then this function is going to output a loss, a gradient for each parameter between layers, and then the last hidden state. So what is a forward pass? So the forward pass in a recurrent network looks like this. This function describes the forward pass, or this function describes how the hidden state is calculated. Right, so how is the forward pass calculated? So the forward pass is, remember, it's just a series of matrix operations. So this is basically our forward pass right here, what you're looking at right here. So this first equation right here is let me make this smaller so you can see. So the way we compute this math operation right here, this is the forward pass, is the dot product between the input to hidden state weight matrix and the input data, that's this term right here, plus the dot product between the hidden state to hidden state matrix and the hidden state, and then we add the hidden bias. And that's going to give us the hidden state value at the current time step, right? So that's what that represents. And then we take that value and we feed it, we compute the dot product with the next weight matrix, and that is the hidden state to the output, and then we add that output bias value, and that's going to give us the unnormalized log probabilities for the next chars, which we then squash into probability values using this function p, which is actually right here, p right here. But I'll talk about that in a second, okay? So that's our forward pass. And then for our backward pass, the backward pass is going to be, before I talk about the backward pass, let's talk about the loss for a second. So the loss is the negative log likelihood. So it's the negative log value of p, and p is this function here. So, which is represented programmatically by this right here, right? So it's it's e to the x, where x is the output value from that it received, divided by the sum of all of the e to the probability values. Okay, and that's going to give us a p value, okay? And so we take that p value, and then we take the negative log of that p value, and that is our loss scalar, that loss scalar value. And so once we have that loss, we're going to perform backpropagation using that loss. And so the way we compute backpropagation, to go over this, is by using the chain rule. So the chain rule is from calculus. What we want to do is compute gradients for each of the layers, okay? So for each of the weight matrices, okay? Given an error value, we're going to compute the partial derivative of the error with respect to each weight recursively. So the reason we're using the chain rule is this. So because we have three weight matrices, we have the input to hidden, hidden to output, and hidden to hidden, we want to compute gradient values for all three of those. So that's what this looks like. We want to compute gradient values for all three of those weight matrices. And the way we're going to do that is to compute our loss using the negative log likelihood, and use that loss to compute the partial derivative with respect to each of these weight matrices. And once we have those, that's our gradient value, that's the change, that's the delta. We can then update all three weight matrices at once, and we just keep doing that over and over again. So our first gradient of our loss is going to be computed using this function. So compute p minus 1, and that's going to give us our first gradient, and we're going to use the chain rule to backward pass that gradient into each into each weight matrix. So let me talk about what I mean by this. So the chain rule, so remember how I said neural networks are giant composite functions, right? It's a giant composite function. And what the chain rule lets us do is it lets us compute the derivative of a function as the product of derivatives of its nested functions. So the chain rule in the case of f of x right here, if f of x is a composite function that consists of g of h of x, then the chain rule would be to say, well, let's compute the derivative of g of h of x times the derivative of h of x, that nested function. So you multiply it by the derivative of the inside function, and that will give you the derivative of that bigger function. Okay, and you keep doing that for as many nested functions as you have. Here's another example. If I want to derive the function 3x plus 1 to the fifth, then I would say, well, this is actually a function, and the function is, the outer function g of x is 3x plus 1 to the fifth. So using the power rule, we take the exponent value, move it to the coefficient, and then subtract 1 from the exponent. So then it would be 5 times 3 of x plus 1 to the fourth times the derivative of the nested function, which is 3x plus 1. And that's the chain rule. And if we multiply those two derivatives together, that will give us the derivative of the larger function f of x. So that same logic applies to neural networks because neural networks are composite functions. So we are recursively moving this derivative, this partial derivative value, by moving, I mean multiplying, dot product. We're computing the dot product between the partial derivative calculated at the last layer, and we're multiplying it by every layer recursively going backward. This will make more sense as we look at this programmatically, but that's what's happening here. And yeah, that's what's happening here. So let's code this out. By the way, the bias, the reason we add a bias is it allows you to move think of it as like this, you know, in the y equals mx plus b equation, it allows you to move the line up and down to better fit the data. Without b, the line will always go through the origin 0, 0, and you might get a poorer fit. So a bias is kind of like an anchor value. Anyway, to define our loss function is going to be, so we're going to give it our inputs and our targets as its parameters, as well as the hidden state from the previous time step. Okay, so then let's define our parameters that we're going to store these values in. So I'm going to define 4 parameters. Okay, these are lists that we're going to store values at every time step in, okay, as we compute them. So these are empty dictionaries. So xs will store the 1-hot encoded input characters for each of the 25 time steps. So this will store the input characters. HS is going to store the hidden state outputs. Okay, YS will store the target values, and PS is going to take the Ys and convert them to normalized probabilities for chars. Okay, so then let's go ahead and say HS, the value of HS is going to be, the reason we're copying this, so check this out. We're going to initialize this with the previous hidden state, the HS currently with the previous hidden state, and using the equal sign would just create a reference, but we want to create a whole separate array. So that's why we don't want HS with the element -1 to automatically change if H previous is changed. So we'll create an entirely new copy of it. And so then we'll initialize our loss as 0, and then okay, so we'll initialize our loss as 0. So this is our loss scalar value, and then we'll go ahead and do the forward pass. So the forward pass is going to look like this. Okay, so we've already looked at it mathematically, and now we can look at it programmatically. So we'll say, okay, so for each value in the range of inputs, so for the length of inputs, let's compute a forward pass. So the forward pass is going to be we're going to start off with that 1 of k representation. We place a 0 vector as the teeth input, and then inside that teeth input, we use the integer in inputs list to set the correct value there. Okay, so that's on that second line. And then once we have that, we're going to compute the hidden state. Now remember, I showed you the equation before. We just repeat that equation here. And then we compute our output, just like I showed before. And then our probabilities, the probabilities for the next chars. Once we have our probabilities, we'll compute our softmax cross entropy loss, which is the negative log likelihood. It's also called the cross entropy. You'll actually see that in TensorFlow, the cross entropy as a predefined function, but we're computing it by hand here. And so once we have the forward pass, now we can compute the backward pass. We're going to compute the gradient values going backwards. So we'll initialize empty vectors for these gradient values, right? So the gradients, the gradients are the derivatives. The derivatives are our gradients. It's the same thing here. So we're computing our derivatives with respect to our weight values from x to h, from h to h, and then from h to y. And we'll initialize them as zeros. And then we also want to compute partial derivatives or gradients for these bias values for our hidden state and our output. And then as well as for our next, which means the next time step, the hidden state in the next time step, derivatives for all of them. When we do backpropagation, we're gonna collect our output probabilities and then derive our first gradient value. Now our first gradient value, it looks like this. Let me go back up here. This is how we compute our first gradient value with respect to our loss, right? That's a first gradient value. So we're going to compute the output gradient, which is the output times the hidden state's transpose. And we can think of this, so look, check this out right here. So this is our first partial derivative for our hidden state to y, to our output layer, that matrix. And so what we do is we compute the dot product between that output and the transpose of the hidden state. The reason we use a transpose is we can think of this intuitively as moving the error backward through the network, giving us some sort of measure of the error at the output of that layer. So when we compute the dot product between the transpose of some layer's matrix with the derivative of the next layer, that is moving the error backwards. It's backpropagation because the error value, it's constantly changing with respect to every layer that it moves through. And by multiplying it by the transpose of a layer, the dot product from the partial derivative with the previous layer times where we currently are, it's going to output a gradient value, that derivative, right? And we'll use that derivative later on to update other values as well. So we're also going to compute the derivative of the output bias, and then we're going to backpropagate into h. So notice how we are continuously performing dot product operations here for every single layer we have. We're also backpropagating through the tan h nonlinearity, right? So we are computing the derivative value, and this is programmatically what the derivative of tan h looks like. And we're using the computed derivatives from the previous layer that we were at the end of the network, the tail end, as we move through to the beginning, as we're using them as values to compute the dot product of. The whole point of computing the dot product with these, with respect to each of these layers, is that we are computing new gradient values that we can then use to update our network later on. So then we use that raw value to update our hidden value, and then lastly we compute the derivative of the input to the hidden layer, as well as the derivative of the hidden layer to the hidden layer. And once we have that, we can return all of those derivatives, our gradient values, our change values. We can return all of that. Now, there's also this step right here to mitigate exploding gradients, which we're not going to go into right now because it's not really necessary. However, I will say this, that whenever you have really, really long sequences of input data, like the Bible, just a huge book, then what happens is as the gradient is moving, by moving I mean you're computing the dot product of it for every layer with the current weight matrix wherever you're at, using the partial derivative, the gradient value will get smaller and smaller. It's a problem with recurrent networks that's called the vanishing gradient problem. Okay, and so it gets smaller and smaller, and there's a way to prevent that. One way is to clip those values by defining some interval that they can reach, or another way is to use LSTM networks, which we're not going to talk about. But anyway, yeah, so that's our forward and backward pass. We computed that inside of the loss function, and we computed our loss as well right here using softmax cross entropy. So for as many characters as we want to generate, we will do this. So we'll say the forward pass is just like we did before. It's the same exact thing. It's just repeating the code over and over again. Input times weight, activate, repeat, get the probability values, pick the one with the highest probability, create a vector for that word, customize it for the predicted char, and then add it to the list. And we just keep repeating that for as many, n defines how many characters we want to generate. So we can generate as many characters as we want on a trained network, and we'll print those out. Okay, so then for the training part, we've completed that meat of that code, right? But now for the training part, we're gonna feed the network some portion of the file, and then for the loss function, we're gonna do a forward pass to calculate all those parameters for the model for a given input-output pair, the current char, the next char, and then we're gonna do a backward pass to calculate all those gradient values. And then we're gonna update the model using a technique, it's a type of gradient descent technique called attograd, which is it just decays the learning rate, but it's gradient descent. You'll see what I'm talking about. It's not complicated, but it's called attograd. So we're going to create two arrays of chars from the data file. The target one is going to be shifted from the input one. So we basically just shift it by one, as you notice here. So now we have our inputs and our targets, right? And these numbers are actually character values in the dictionary, but they represent, they help us create vectors where the indices here represent the one out of all the zeros and the zero vector. And that's what we feed into our model. So attograd is our gradient descent technique. And the difference here as compared to regular gradient descent is that we decay the learning rate over time. And what this does is it helps our network learn more efficiently. This is the equation for attograd, where a step size means the same thing as a learning rate, but basically the learning rate gets smaller during training because we introduce this memory variable that grows over time to calculate the step size. And the reason it grows while the step size decreases is because it's inside of the denominator of this function right here. This is the programmatic representation of the mathematical equation that you're looking at right here. So here's the programmatic implementation of that. We calculate this memory value, which is our gradient, right, of our parameters, and then we update our weight matrix conditioned on the learning rate, which decays over time via this function right here. So finally, so we've done all the math, and now it's just implementing it. So we have our weight matrices here. We have our memory variables for attograd. And then we will say for 1,000 iterations, well, actually 1,000 times 100 iterations, we want to feed the loss function. We want to feed the loss function the input vectors to see how this part works. We're going to feed the loss function our input vectors, and then we're going to compute a forward pass using that loss function, and it's going to compute the loss as well. It's going to return the loss function or the loss scalar. It's going to return the derivatives or gradients with respect to all of those weight values that we want to update. And then we're going to perform the parameter update using attograd, right? So we'll feed all those derivative values to our attograd. This is attograd. So we'll feed all those derivative values to our attograd function right here. Okay, and it's going to update our parameters, and basically the learning rate just decays over time. That's why MEM is calculated, to decay the learning rate over time, and which just helps with convergence. And there's different gradient descent techniques, Atom, and different ones like that, but momentum, but yeah, attograd is one of them. And so once we do that, we can look at our sample function here, and our sample function is going to, right here, we're gonna generate 200 character sentences at a time for 1,000 times 100 iterations. So a lot of iteration, 100,000 iterations. Okay, so let's go ahead and run this and see what happens. Okay, see, the first iteration is really bad. Look at that, it's just like weird characters. Okay, but now it's got more human readable characters. Okay, it's getting better. Now it's like he ate leth. Notice how the loss is decreasing very rapidly here as well, okay? And so, yeah, it's getting better over time. Okay, so that's it for our network. And let me stop this. And you can feed it anything, really. You can feed it any text file. It's going to work with any text file. Okay, so we've computed the forward pass, the backward pass. The backward pass is just the chain rule. Okay, I've got links to help you out in the description, but it's just a chain rule. We're just continuously computing derivatives or gradient values partial derivatives or gradients, same thing. We call them partial because they're with respect to each of the weights in the network going backward. And we are moving this error, by moving, we're computing the dot product of each layer's matrix by the derivative of the previous layer, just continually, and that's the chain rule. And if we do this, we can generate words. We can generate any type of word we want to, given some text corpus. You can generate Wikipedia articles, you can generate fake news, you can generate anything, really, code. And yeah, so also for deep learning, you might be asking, well, for deep learning, which of these layers do we add where do we add deeper layers to? Do we add more layers between the input and the hidden state, between the hidden state and the output, or between the hidden state and the hidden state matrix? Which direction do I add deeper and deeper layers? Well, the answer is that it depends. This is one thing that's being worked on, but the idea is that you'll get different results for whatever set of matrices that you add deeper layers to. There are different papers on this, but yes, adding deeper layers is going to give you better results, and that's deep learning. Recurrent net's applied to deep learning, but this is a simple 3-layer feed-forward network that works really well, and I would very much encourage you to check out the GitHub link in the description and the learning resources to learn more about this. So yeah, please subscribe for more programming videos, and for now, I've got to do a Fourier transform. So thanks for watching.